This is part 2 of the boot MIPS code walkthrough. The init GIC code works around getting information and setting bits in the Global Interrupt Controller, or GIC for short. The GIC address space is accessed with uncached load and store commands. For each load or store command, the hardware supplies the physical address along with the processor number of the requester. The processor number is used as an index to reference the appropriate subset of the instantiated control registers. By using the processor number information, the hardware writes or reads the correct subset of control registers pertaining to the local CPU. Software does not need to explicitly calculate the register index for the local CPU core. This is done entirely by hardware. The GIC is divided into sections. The first section starts at the base address of the GIC. This shared section is where the external interrupt sources are registered, masked, and assigned to a particular processing element and interrupt pin. This section is used by all processors. Next is the local section, which starts at the base address plus 8000 hex. This is the section in which interrupts local to the processor are registered, masked, and assigned to a particular interrupt pin. The local CPU can access registers of another CPU core by using the core other address spaces. Software must write the other address register before accessing these address spaces. The value of this register is used by hardware to index the appropriate subset of control registers for the other processor. An additional section called the user mode visible section is used to give a quick user mode read access to specific GIC registers. The use of this section is meant to avoid the overhead of system calls to read GIC resources such as counter registers. Back in the start.s, the code calls init GIC. Then, in the init GIC function, the code checks to see if it needs to initialize the global interrupt controller. It checks GPR11, and if it is not set, then this is not a coherent processing system, so the code will skip the GIC initialization. To check to be sure if there is a GIC, the code reads the global control block's GIC status register. It extracts the GIC EX bit and then tests to see if it's set. If it is not set, there is no GIC, so the code will skip the GIC initialization. There are two parts of the GIC that needs to be initialized. A shared part that needs only to be initialized by CPU 0, and a local part that needs to be initialized by each processor. The code will do the shared part only if it is CPU 0, so it checks GPR23, the CPU number, and will skip the shared section if it is not 0. The code loads the address of the GIC base address register into A1. As you can see from the table, the address is on a 128K boundary, so the lower 7 bits will always be 0. This leaves space for additional information in the register. The GIC EN field controls the enabling of the GIC. The code loads A0 with the address of the GIC. Note, this is a physical address ORed with 1 to enable the GIC. Next, it stores the value into the GCR GIC base register. The code will use the GIC configuration register to confirm how many external interrupt sources we have. To do this, the code will read the register and isolate the num interrupts field, bits 16 through 23. Interrupt sources are configured in the core in groups of 8. This field tells us how many groups of 8 minus 1 the core has. To do this, the code loads the defined GIC base adder, which is the starting address of the shared section of the GIC, into A1. The shared configuration register shown above is located at offset 0. The code loads its value into A0. The code then extracts the number of interrupt groups. The code loads the expected value into A3, so it is expecting 40 interrupt sources, 4 plus 1 times 8. If the code doesn't get what it expects, it executes a debug breakpoint to stop at this point, where you can use the debug probe to see what's going on. To disable interrupts, the code will use the global interrupt reset mask registers. Each interrupt source has a corresponding bit in a reset mask register. Setting the bit to 1 resets and disables the interrupt in the GIC. The GIC can control up to 256 interrupt sources. Since all the registers in the GIC are 32 bits wide, to have enough bits to cover the 256 sources, we will need 8 reset mask registers. The first register will control interrupts 0 through 31. The second will control 32 through 63, and so on. The system in our example has external interrupts connected to sources 24 through 39. These interrupt sources will use the first 2 global interrupt reset mask registers. The code that follows configures the interrupts one section at a time. First, it will configure interrupts 24 through 31, then 32 through 39. The code disables interrupt sources 24 through 31 by writing a 1 to bits 24 through 31 in the first global interrupt reset mask register. There is a set of registers that configures the trigger type of the interrupt. Setting the corresponding bit causes the interrupt to be treated as edge signaling. If the bit is cleared, the interrupt is level signaling. The offset of the global interrupt trigger type register in the GIC section is hex 180. The code uses A0 to write 1s to bits 24 through 31 of the first interrupt trigger register. This configures interrupt sources 24 through 31 to be edge sensitive, which is needed to support interprocessor interrupts. Similar to the reset mask registers, there is a set of registers that configures the polarity of the interrupt. The polarity determines how the interrupt is signaled to the core. Interrupts can be level or edge sensitive. If level sensitive, setting the interrupt's corresponding bit to 1 will configure it active high, and setting it to 0 will configure it active low. If the interrupt is edge sensitive, setting the corresponding bit to 1 will configure the interrupt on the rising edge, and setting it to 0 will configure the interrupt on the falling edge. The offset of the global interrupt polarity registers in the GIC is hex 100. The code uses A0 to write 1s to bits 24 through 31 of the first interrupt polarity register. This configures interrupt sources 24 through 31 to be rising edge sensitive to support interprocessor interrupts. There is a set of registers that corresponds to the global interrupt reset mask registers. These are the global interrupt set mask registers. Where the reset mask registers disable interrupts, the set mask registers enable interrupts. The code sets the same bit still in A0 as it did for the polarity registers to set the enabled bits 24 through 31. This section of code configures interrupts 32 through 39 in the same way it configured interrupts 24 through 31. The configuration registers that control this range of interrupts is the second register of each set, so you can see the code is offsetting each register by an additional 4 bytes. Interrupts 32 through 39 are located in the 8 lower bits of the registers, so the code sets A0 to hex FF, and will use this register to set interrupts 32 through 39 bits. Then the code disables interrupts, sets the polarity register, sets the trigger registers, and at last enables the interrupts. The code will configure which processor a particular interrupt will be assigned to. To do this, the GIC has registers for each interrupt source. Each bit in those registers corresponds to a processor in a multi-core system. For example, for interrupt source 1, bit 0 would assign the interrupt to processor 0. The current scheme supports up to 64 different processors, so there are 2 32-bit registers for each interrupt. To allow for future expansion, the registers are spaced 32 bytes apart. Let's look at the table. The interrupt map to VPE registers are in the GIC shared section and start at offset 2000 hex. The first interrupt has its registers at 2000 hex and 2004 hex, thus giving it a 64-bit map area. The next interrupt starts at the start of the section plus 32 bytes, or 20 hex, so its registers are at 2020 and 2024 hex, and so on. There is a convention in MIPS Linux to use the last 16 interrupt sources for interprocessor interrupts. In the system we are configuring, those are interrupts 24 through 39. The system could contain up to 8 processors. The code assigns 2 interrupt sources to each processor in the system. The corresponding bit number for a processor is stored in A0. A0 is primed with a 1 for the first processor, processor 0. Then the code stores the value in A0 to the appropriate map registers. The interrupt sources are divided into 2 groups, one group from 24 through 31 and the other group from 32 through 39. The code will take one interrupt source from each group and program it to a processor. Let's go over how the addresses for the GIC map to VPE register is calculated. Previously, the GIC base adder was stored into A1. Remember, this is a pound define in boot.h. The code also uses defines which come from cps/cps.h. The GIC sh map 0 VPE 31 through 0 is the base offset of the GIC map to VPE registers. The GIC sh map spacer is the size or space between each interrupt's GIC map to VPE register. The calculation is the base address of the GIC registers offset by the base offset of the GIC map to VPE registers plus the space between the interrupt registers times the interrupt number. The code continues to program each processor in turn. To increment the processor number stored in A0 to the correct bit position, it will shift A0 and program the appropriate map registers for the next interrupt pair. This next section of code will initialize the per processor elements of the GIC. The section of registers being initialized is called VPE local and is located at the GIC offset of 8000 hex. The code reads the local interrupt control register into A3. the code will be using some of the values from this register. The code checks to see if the timer interrupt is routable. It does this by extracting the timer routable bit from the control register value it had previously read into A3. Then it checks to see if it's set. If it is not set, the timer interrupt is not routable and the code will branch around routing it. The code sets up A0 with the encoding that is used to route the local CPU timer interrupt to the desired processor pin. A0 is written with bit 31 set and a 5 in the map field. This will map the local core's timer interrupt to the current processor unit's interrupt pin 5. This value is stored to the GIC local CPU timer map to pin register. As it did with the timer interrupt, the code checks to see if the performance counter interrupt is routable. It does this by extracting the performance counter routable bit from the control register. Then it checks to see if it is set. If it is not set, the performance counter interrupt is not routable and the code will branch around routing it. The code sets up A0 with the encoding that will map the performance counter interrupt. A0 is written with bit 31 set and a 4 in the map field. This will map the local core's performance counter interrupt to the current processor's interrupt pin 4. This value is stored in the GIC local CPU performance counter map to pin register. This ends the GIC configuration. Back in start.s, the code is done initializing each processor. It continues to see if it is VPE 0 or processor 0. If it is not, then it is done with the initialization and will branch to init done. The code is about to initialize the iCache and then enable caching. It initializes the Dcache and the L2-3 caches after enabling caches because the code will run faster for those functions once the iCache is enabled. For all this to work correctly, the L2-3 caches must be disabled until they are initialized. So at this point, the disable L2-3 function is called to do that. To disable the L2 cache, the CCA override enable bit will be set. This is bit 4 of the GCR base register. The code checks to see if it is executing on a coherent processing system, and if it is not, it will branch around the next piece of code and assume there is no L2 cache. The code reads the GCR base register. The next 3 lines of code are used to enable the CCA override and set the L2 CCA to non-cached. Next, the init iCache function is called. I'm not going to go over the init iCache initialization code in this class because it's already been covered in the basic software training class. Now that the iCache has been initialized, we can take advantage of it and change the CCA of kseg0 to be cached. One important thing to note is that changing of the CCA of kseg0 must be done from kseg1, which is a never cached segment. The code loads the address of the change k0 CCA function. Then it changes it to an address in kseg1 segment by inserting a 1 into bit 29. When the JLR executes, it will jump to this uncached segment, execute the code changing the CCA of kseg0, then jump back to this code and start executing from the iCache. The changing of the K0 CCA function is a function common to all MIPS cores, so there is a little runtime decision to be made to set the correct CCA. The code uses a cache write-back CCA of 3 for non-coherent cores and a cache coherent write-back CCA of 5 for coherent cores. To do this, it simply checks to see if the R11 is CPS register is not set. If it is not set, it stores the non-coherent CCA to V1 in the branch delay slot and branches to the setting of the config register code. If it is set, it falls through the branch and stores the CCA value for the coherent cores into V1 and continues to the setting of the config register code. The value of V1 is inserted into bits 0 through 3 of the stored value of the configuration register and then written to that register. The code uses a JRHB instruction that will clear the hazard barrier and make sure that the configuration register write has been completed and then jump back to the calling function. Next in start.s is a call to initialize the D-cache. That is also covered in the Programming a MIPS Core software course, and I'm not going to cover it here. The init ITC is a placeholder for you to put any code you need to initialize the ITC for your system. At this point, the code will continue to initialize system-wide resources. Since this only needs to be done by only one processor, the code tests to see if it is executing on core 0. If it is not, it will jump to done. If it is, it will continue the boot and initialize system resources. Back in start.s, in the init sys resources section, the init CPC is called to initialize the cluster power controller. In the init CPC function, the code first checks to see if this is a coherent processing system by checking R11 is CPS. If it is not, then it will not have a CPC, so it will skip to the end and return. If this is a CPS, then the code will check to see if there is a cluster power controller. It does this by checking the cluster power controller status register. This register is located within the global configuration registers at offset F0 hex. The code uses the previously stored address of the GCR base and the defined GCR CPC status as an offset to read the cluster power controller status register into A0. There is only one field in the cluster power controller status register called CPC-EX, and if that bit is set, then the CPC is connected to the CPS. The code singles out bit 0 of the GCR CPC status value. If it's 0, then there is no CPC and it branches around this code and returns to the initialization function. In the branch delay slot, we ensure GPR30 is cleared to indicate we don't have a CPC. If there is a CPC, the code will set the address of the CPC in the cluster power controller base address register. The address of the cluster power controller base address register is at offset 88 hex of the global configuration registers. The code uses the known value of where the CPC is within the system and writes that to the cluster power controller base address register. Note, this is a physical address. Then the code stores this address for later use in GPR30 using the KSEG1 equivalent address, and it is done setting up the CPC. Now the code calls initcm to initialize the coherency manager. First, the code checks to see if it is booting a coherent processing system, and if not, it will branch to the end of this function. The lower 8 bits of the global CSR access privilege register controls the write access to the GCR registers by a processor. If a bit is set, then the processor can change the GCR. The code here is rather clever. First, it loads a 2 into A0. Then the code shifts the 2 to the left by the number of processor units minus 1. For example, if there were 4 processors in the system, then GCR19 would contain a 3. 2 shifted left by 3 is 16, or 10 hex. Now the code subtracts 1, so again, assuming 4 processors, 16 minus 1 is 15, or F hex. So now we have all 4 lower bits set. The value is written to the global CSR access privilege register, which will now allow all 4 processing units to change the GCR. This code checks to see if there is an IOCU. It does this by loading the GCR configuration register into A0, extracting the num IOUC field as shown in the table above. Then it jumps around the next section of code to the end of the initCM function if there is no IOCUs in the system. If there is an IOCU, the code will disable the IOCU regions. The code loads an upper immediate value into A0. This value sets bits 16 through 31 and clears bits 0 through 15. As you can see from the table, the lowest bit, bit 0, set to 0 will disable the CM region. The code uses A0 to store the value to all CM regions and thus disables them. This completes the CM initialization, and the code returns to init sys resources. In start.s, a call is made to initialize the memory controller.